Hello everyone, I am Gr8, pursuing post-graduation in Construction Engineering and Management from SEPT University. My student code ID is PCM25125 and I will be presenting about the project feasibility study in the SEM1, which is about construction project formulation and appraisal. Today I'll be presenting the construction of a flyover at Forum Junction. This 652-meter greenfield project is proposed by the municipal corporation and funded by the state government. The flyover aims to address a severe congestion at a junction that connects major urban roads and carries constant mixed traffic. The objective is to enable smooth, signal-free movement by separating through traffic from the intersection, thereby reducing delays, improving safety, and strengthening overall mobility. The scope of work includes approach roads, the flyover, utility shifting, environmental management, footpaths, service roads, and planned underspace development. The project also supports pedestrian safety, reduces idling and conflicts, removes encroachment, and enhances last mile connectivity across important city links such as highway and Sabarmati corridor and the surrounding residential and commercial zones. In the second slide, we move on to risk identification. A total of 125 risks were identified for the project, in which 120 of them were threats and only 5 are opportunities. The bar chart categorizes risk across political, economical, technological, social, environmental, legal, construction, design, and management domains. The highest risk concentration is under management risk with 27 risk, followed by construction risk with 16 risk and environmental risk with 14. These risks represent typical challenges in urban flyover projects such as land use, approvals, traffic disturbance, utility shifting, obstruction of overhead lines, and public sensitivity. This systematic identification lays a foundation of prioritizing what can delay or disrupt the project and what opportunities can be leveraged. These slides explain how each risk can be analyzed in terms of response and ownership. Most risks fall under the mitigation category, which means they require proactive planning and continuous monitoring. A few high-impact risks are placed under avoid, meaning the design or the methodology must be changed to eliminate them. When assigning responsibility, we see that the contractor owns a majority of the risk since most issues arise during construction. The client is second highest owner because they manage approvals, fundings, and land matter. Critical risk includes waterlogging, loss of green cover, alignment issues, improper curing, and accidents, all of which are significantly impact time, cost, and safety. Clearly defining risk owners ensure accountability and better coordination throughout execution. Here, the risks are plotted on severity matrices for both threats and opportunity. High probability and high impact threats include poor safety facilities, traffic diversion issues, undetected utilities, labor shortages, cost overruns, and political delays. These require continuous oversight because they can directly cause accidents, design failures, or stoppage of work. Medium probability risks such as waterlogging, loss of green cover, public inconvenience require monitoring to avoid escalation. Rare but high impact risks such as sinkholes, cash flow interruptions, and changes in political power carry low probability but could be severe consequences if they occur. On the opportunity side, the project benefits from using recycled aggregates, local materials, job creation, and economic stimulation around the junction. This matrix helps the team understand where to dedicate the most time, resources, and attention. This slide introduces the choosing by advantage method for selecting the appropriate bearing type for the flyover. 3 bearings were evaluated: elastometric, pot, and roller sliding bearings. Each was assessed on friction, load capacity, rotation, maintenance, movement, service life, and temperature stability. Roller slides bearing achieved the highest importance of advantage score, but their cost per unit is nearly thrice that of pot bearing. Considering a flyover length, span, and load characteristics, pot bearings offer an optimal balance between the performance, durability, and cost efficiency. Therefore, pot bearings are recommended for this project, ensuring reliable behavior under traffic loads, and thermal variation. In this slides, we apply the CBA again, this time to select between a solid deck slab and a hollow core slab. The hollow core slab achieves a significantly higher score due to the reduced self-weight, less concrete consumption, decreased deflection, lower material usage, and better structural efficiency. It also offers improved lifespan and faster construction due to its precast and lightweight characteristics. Although solid slab offers strength and simplicity, the hollow slab outperforms across almost all criteria and is more cost efficient for the span and usage conditions of this flyover. Therefore, the hollow slab is chosen as a preferred deck option. Design brief. This slide outlines a design brief based on IRC and IS codes. The flyover consists of substructure components, pile caps, pier caps, and superstructure elements such as bearings, girders, deck slab, bearing cord, and expansion joints. The design methodology involves defining the scope of work, preparing specifications, checking compliance with IRC and IS codes, and engaging key stakeholders for primary data like soil conditions, utility details, and traffic patterns. These codes guide the geometric design, loading considerations, reinforcement detailing, and drainage planning, ensuring that the structure remains safe, durable, and serviceable throughout its life. This slide focuses on the drainage system and the main superstructure elements. PSC1 girders with a 20-meter span form the primary load-carrying structure. The deck slab is cast in situ with M25 concrete and reinforcement using FV500 steel. The drainage system is designed with a 2.5% crossfall and includes IRCC or precast channels with gratings. The GI scarpers, vertical downpipes, and UPVC runners. Collected water is carried through NP4 stormwater pipes to the nearest municipal drainage line, ensuring that the flyover deck remains dry and safe during rainfall. A dedicated 600 mm utility corridor runs under the footpath, accommodating electricity, water, and telecom lines without disrupting traffic during maintenance. This slide highlights the supporting urban infrastructure elements required for safety and functionality. Carriageways are designed with proper lane width, anti-skid paver block footpath, RCC curbs, bollards, delineators, and New Jersey type crash barriers. Parking is organized to reduce roadside congestion, and epoxy coated side drains ensure smooth surface runoff and long time durability. Urban furniture, including benches, planters, signage, bins, and toilets, improve pedestrian comfort and enhances the aesthetics around the junction. Together, these elements ensure that the flyover integrates seamlessly with the urban environment, improving both traffic movement and public usability. In conclusion, this project provided a comprehensive understanding of how engineering management design decisions must work together for a complex urban flyover. Risk management helped identify and prioritize threats such as utility conflicts, political delays, and safety issues, while also recognizing opportunities like using recycled materials. Choosing by advantage provided clarity in selecting the most efficient bearing and deck slab systems, ensuring long-term performance. The design brief guided by IRC and IS codes ensure that every component from pile to crash barriers meets safety, durability, and serviceability standards. Overall, the project demonstrates a structured and evidence-based approach to designing a modern flyover that improves mobility, reduces congestion, and enhances urban infrastructure at a critical junction. Thank you.